In the last class, we have seen what the closure law, associative law, existence of identity, and in the last class, existence of inverse element. We have discussed about the existence of inverse element. So, all these four axioms are said to be group axioms. What the group axioms are? Closure law, associative law, existence of identity element, existence of inverse element. Let G star be an algebra structure. Now, let us discuss about groupoid, semi-group, monoid and group. As these all are group axioms, we have discussed about all these things, and we have to see what is a groupoid and what is semi-group and what is monoid, and finally the group, and another one is Abelian group. Let us first see what is a groupoid is. An algebra structure in which only closure law is satisfied. Only closure law is satisfied. A star B belongs to G. Suppose G star is an algebra structure. A comma B belongs to G. A star B belongs to G. Then we say G star is a groupoid. It is named as groupoid. Only closure law is satisfied. Z minus the set of integers, the binary operation is minus. So, with respect to the binary operation minus, integer minus integer is definitely an integer, no doubt about it. So, closure law is satisfied. With respect to the binary operation excluding multiplication and addition, the minus or divided by the associative law is not satisfied. A minus B minus C is never be equal to A minus B minus C, the set of integers. For any integers A, B, C, A minus B minus C is not equal to A minus B minus C. So, in the similar way, Q divided by. So, we have discussed about the associative law in the previous classes. At that time, I have given these two examples. These are the algebra structures which won't follow the associative law. These two algebra structures follow closure law, but they won't satisfy associative law. So, these two are the only examples of, not only means the only groupoids. These two examples are not only the two examples, there are several examples. These are the examples of only groupoids, and those who satisfy closure law only, right. Suppose group satisfies all the four axioms 1, 2, 3, 4. That is why they are called group axioms. Closure law, associative law, existence of identity, existence of inverse. Since closure law is satisfied in the group can be called as groupoid. Every group is a groupoid. Similarly, semi-group satisfies two laws, closure law and associative law. Closure law and associative are two axioms that are satisfied in semi-group. What about group? In group, all four axioms are satisfied. So, every group is a semi-group, but every semi-group cannot be group. Every groupoid cannot be group. Every group is a monoid. Monoid means that satisfy closure, associative, existence of identity. Three axioms, first three axioms. That is said to be monoid. So, every group is a monoid, every group is a semi-group, every group is a groupoid. Every semi-group is a groupoid. Every monoid is a semi-group, likewise. So, these two are only groupoids. Every group is a groupoid, but this is the examples of groupoid. Example of groupoid which is neither semi-group nor monoid or something. So, the only examples of groupoids. Examples of groupoid only, right. In this way, semi-group. An algebra structure in which closure law and associative law are satisfied is said to be semi-group. In the group theory, we have important concepts are, we won't use these groupoid and monoid, semi-group, group, Abelian group, all these are very, very important. So, what is semi-group? An algebra structure in which closure law and associative law are satisfied, that is said to be semi-group. Let us see the examples. N plus natural numbers with respect to addition. The natural numbers with respect to addition, closure law is clearly satisfied, associative law is satisfied. What about the identity element? With respect to binary operation plus, identity element is 0. 0 does not exist in set of naturals. Therefore, This algebra structure satisfies only two binary operations, closure law and associative law, which is a very good example for only semi group. Similarly, 2z dot. What is 2z? We have discussed in the previous classes. That is a set of all even integers or multiples of 2. Set of even integers. So, 2, 4, 6, 8, minus 2, minus 4, 6, 8, which includes 0 also, but this is with respect to multiplication. Product of two even integers is an even integer. Associated law with respect to multiplication easily satisfied, but with respect to the binary operation dot, what is the identity element? 1 is the identity element. 1 does not exist in 2z. Therefore, 2z dot is the algebra structure which satisfies only closure law and associative law. Therefore, this is a semi group only. Similarly, 3z dot is semi group only. Only semi group means these three are not only the examples of semi groups. These are semi groups only. They won't go further. They cannot be monoids. They cannot be groups. These are the examples of only semi groups, right? Monoid, an algebra structure in which closure law, associative law and existence of identity element are satisfied. First three axioms, closure, associative and identity. So, examples, whole numbers with respect to addition. With respect to addition, the sum of two whole numbers is a whole number, and associative clearly holds with respect to addition, and additive identity is 0 in whole numbers, natural numbers and 0 are there. Therefore, W plus satisfies closure, associative and inverse. Closure, associative and identity element 0. This is a monoid. Z dot, integers with respect to multiplication. So, on multiplying to any two integers, either positive or negative, any two integers, we get an integer. Associative law with respect to binary operation, multiplication, associative clearly satisfies, and identity element 1 is there in Z. So, multiplicative identity is there. Inverse, the inverse of 2 is 1 by 2, the inverse of minus 5 is minus 1 by 5. So, inverse does not exist, only closure, associative and existence of identity. So, this is a clear example of a monoid. Similarly, n dot, natural numbers with respect to multiplication. Product of two natural numbers is natural, associative law holds, and identity 1 is identity element, multiplicative identity 1 exists in n. Therefore, first three axioms, closure, associative and existence of identity satisfied in n dot. Inverse does not exist for all natural numbers with respect to multiplication. Therefore, W plus Z dot, N dot are some examples of monoids. Only monoids, they cannot be groups, monoids only. First three axioms are satisfied. So, finally, let us go for group, an algebra structure G star in which 1, 2, 3, 4. What the 1, 2, 3, 4 are? Closure law, associative law, existence of identity element and existence of inverse. All the 4 group axioms are satisfied, then that algebra structure is said to be a group. Clear? We are clear. Z plus is a group, Q plus, R plus, C plus, Q dot, R dot, C dot. What I have already told you, when you consider groups with respect to multiplication, the inverse axiom, we have to consider the inverse axiom with respect to non-zero element. For every non-zero element, if there exists an inverse in Q, for every non-zero element, if there exists an inverse in R, for every non-zero complex number, if there exists an inverse, then we say these are groups. Clear? For 0, we won't verify the inverse with respect to multiplication. Right? This is about group theory. There is another axiom which is said to be, what is that? Commutative law. Let us see that. Commutative law. G star B, an algebraic structure, right? A and B belongs to Z. let A and B, A comma B belongs to G. If A star B is equal to B star A, then we say commutative law hold in G or G star. Okay. Then G star is, if a group satisfies the commutative law, then we say that group is an abelian group. Let us take that example, abelian group. G star be an algebraic structure. If G star be a group, so 1, 2, 3, 4 axioms are already satisfied. If A star B is equal to B star A in Z, then G is called an abelian group. Abelian. It is also called commutative group. Abelian group or commutative group. Since commutative law is satisfied in a group, that group is said to be commutative group or abelian group. Can we give some examples? Yes, we can. The group examples: Z plus, Q plus, R plus, C plus, and multiplicative groups Q dot, R dot, C dot. All these are the examples I have given to groups are becoming abelian groups. Commutative laws are satisfied in these all examples. So, commutative groups, abelian group or commutative group. Non-abelian, we have to see non-abelian group or non-commutative group. Non-commutative group. For that, we have to seek some special examples. So, these are the fundamentals of group. The non-abelian and non-commutative group we can connect when we discuss about rings, different examples of rings, abelian rings, commutative rings, like that. In that particular example should be there for non-abelian or non-commutative groups. So, we can cover when we go for ring theory so easily. Simple example, A, B are two matrices. A and B are two matrices. The product of A and B never be equal to B and A. Or if we consider the group with common addition, common multiplication, it is very easy to verify commutative law clearly holds. With other binary operation, they won't become groups also. So, this is one of the best examples. A and B are two matrices. A into B is not equal to B into A. Matrix multiplication is non-commutative. If we consider set of all matrices, M is set of all matrices. In M, every element is a matrix. So, consider two matrices, A comma B belongs to M. AB not equal to BA. This is a best example for a non-commutative group with respect to multiplication. M with respect to multiplication, M dot. M dot is non-commutative group. Non-commutative group or non-abelian group. Okay. In the next class, as the fundamentals of group axioms are discussed, we have discussed about group, semi-group, groupoid, monoid, and all these things we have covered. We can jump to ring theory in the next class. Let's meet in the next video.